This is problem 1 of exam 1 in module 6 from the book Problem Solving Guide for Mechanics and Thermodynamics. Problem 1, we have a 4 kilogram mass moving at 5 meters per second towards a 2 kilogram mass. There's a spring here that's going to ensure the collision is elastic, no thermal energy is generated. The spring has a stiffness of 32 newtons every centimeter. When the 4 kilogram mass hits the 2 kilogram mass, the spring is going to be compressed. The question asks, when the 4 kilogram mass has slowed to 3 meters per second, what is the compression of the spring? This problem came with this diagram. Let's label it. There's the 4 kilogram mass. There's the 2 kilogram mass. There's the initial speed. There's a lot going on here. We really have to think. Let's use another snapshot, one in which the spring is compressed and the 4 kilogram mass is moving at 3 meters per second. We need a second diagram, and there it is. The 4 kilogram mass hits the 2 kilogram mass, compresses the spring, and now the 2 kilogram mass takes off. What's the compression of the spring? We have to think. What's going on here? How can we do this? Compression of the spring. We can't get that from conservation of momentum because momentum is only mv. We can assume the collision is elastic, so we're not going to get any heat. We can write the conservation of energy equation and see what happens. So the initial energy is the final energy. The energy in the top picture equals the energy in the bottom picture. E1 equals E2, whatever you want to call it. Initially, we only have the 4 kilogram mass moving at 5 meters per second. Finally, the energy is in 3 places. The 4 kilogram mass is moving, the spring is compressed, there's elastic potential energy, and the 2 kilogram mass is moving. We can calculate the initial energy in the system at 1/2 mv squared, that's 50 joules. The final energy in the system has to be 50 joules. We can write an expression for it. This is the 4 kilogram mass moving at 3 meters per second. This is the elastic potential energy of the spring. Note that we converted from newtons per centimeter to newtons per meter. If it's 32 newtons for 1 centimeter, you need 3,200 newtons to pull it a meter, 100 times as much force. And this is the kinetic energy of the 2 kilogram mass. And we don't know what the speed of the 2 kilogram mass is in that second picture. We have 2 unknowns, x and the speed of the 2 kilogram mass. What do we do now? We have to think. What can we do? Where can we get another equation? Where can we get more information? We used conservation of energy. We know momentum is conserved. The initial momentum in the system is a 4 kilogram mass moving at 5 meters per second to the right. That's plus 20 kilogram meters per second. The final momentum has to be plus 20 kilogram meters per second. The final momentum of the 4 kilogram mass is 4 times 3. To the right, that's 12. We found 12. It started with 20. The 2 kilogram mass has to have 8 kilogram meters per second of momentum to the right for momentum to be conserved. We can set these equal, and we can solve for V2 final, and we get 4 meters per second. So now we have our other unknown. There's the 4 meters per second. We know what's going on. The initial momentum is 20. The final momentum is 20 kilogram meters per second to the right. Now we can use the conservation of energy equation. We know the speed of the 2 kilogram mass. So we had 50 joules initially. We have 50 joules finally. And we can calculate this. That's 18. We can calculate this. That's 16. So we have 18 joules of kinetic in the 4 kilogram mass, 16 joules of kinetic in the 2 kilogram mass. We started with 50 joules. The spring has to have 16 joules of kinetic energy in order for energy to be conserved. There must be 16 joules of elastic potential energy in the spring, and that's 1/2 kx squared, and we can solve for x. 0.1 meters, which is 10 centimeters. This is a challenging problem. If you don't know how to think, you might get stuck. But if you draw a good diagram, situation 1, situation 2, taking a good inventory, you should be able to get through it. That's problem 1.